Good afternoon. My name is Billy McLaughlin. Today we're going to be talking about some Android patchwork. So again, I'm Billy. I work at Independent Security Evaluators as a security analyst. I'm currently working on my master's degree, and I have been for a very long time. Most of all, I'm happy to be back at Derbycon. So Independent Security Evaluators is my employer. We're a small company out of Baltimore. We do security assessments, web assessments, mobile assessments, infrastructure stuff, some white box stuff, some black box stuff, everywhere in between. And a lot of times we need to use some RE. So today we're going to be talking about patching Android applications, why we would want to do that, what we need to do that, and how we're going to go about doing that. First, we need to talk about some terms everyone needs to be familiar with. APK is short for an Android package. It's essentially a zip file that contains everything that is required for the application to function properly. Dex is short for Dalvik executable. It can be thought of as the Android equivalent to a Java class file. The DVM is the Dalvik virtual machine. It can be thought of as the Android equivalent of the Java virtual machine. ART is the Android runtime. As of Android 5.0, I believe, it has replaced the Dalvik virtual machine. A lot of changes happen there, one of which is a move from just-in-time compilation to ahead-of-time compilation. ADB is short for the Android Debug Bridge. This is a command line tool, lets you interact with Android emulators or hardware devices from the command line. You can do things like install packages or open a shell or push and pull files. So today, we're going to be patching this tiny little proof of concept app I developed specifically for Derbycon. It is a Derbycon 6 exclusive. You will never see this anywhere else. We're going to be looking at it from the perspective of a security analyst performing a security assessment. So we're going to want to be looking at this app and examining it to find anything wrong. So, since I wrote this, I know what it does. This application will pin certificates. This means that it is going to be making a secure connection to a website over SSL, and will check the received certificate from the server against a locally stored certificate to determine if the connection is valid. The problem with this, from a security assessor's point of view, is that it can be frustrating in that normally we like to put a proxy in between us and the server so we can view any web requests that are happening, see if there's anything questionable occurring. So this check basically makes that much more difficult because we won't be able to inject our own custom certificate without the application taking a dump. So, what to do? We got a nice little screenshot here. It's got a email field. It's got a password field and a button so you can log in. If you fill in these fields, hit the button without any kind of custom certificates installed on the device, no proxying happening, you'll get a little toast message. It says success, nice cert bud, smiley face. Now, if you want to intercept this traffic before it hits the server, you would install a custom cert onto the device. In my case, it's typically a Burp Suite certificate. And then you would configure the device itself to route all traffic to the Burp proxy. So this is where the certificate pinning will detect a problem. Our application's traffic will be hitting this custom certificate before moving forward to the server. And our application knows that this server certificate should not be what it's receiving. So we're going to get an error. It's going to say failure. Spooky cert detected, sad face. So what are we going to do about this? Well, we want to convince the app to stop caring about what certs it gets and just work. How we're going to do this, we've got a few steps. We want to decompile the application so we can get a human-readable approximation of the original source code. We can do this because Java code is decompiled to an intermediary bytecode that is not machine language. So there are tools that will allow us to go from this bytecode back into something human-readable. We'll be looking at this source code to try to determine where this certificate checking, where the pinning is occurring. We'll be decoding the application so we can get access to the .smali code, which is a representation of the Java bytecode that is somewhat human-readable. And then we will be editing that code to patch it, to do what we want. First step is the decompilation. Our goal is to peep some source code. We have a couple tools we're going to use, the first of which is dex2jar. This is a small program. It will convert the Android classes to the normal Java class style, so then we can use a Java decompiler such as JDGUI or Fernflower, or Procyon, to give us that human-readable approximation of the original source code I mentioned. So the first part of this, we have a APK. It's called patchtown.apk. This is our program. This is our application we're going to be messing around with. We're going to run dex-to-jar on it. That will result in a jar file. You can see it there in red. And then we will run JDGUI on this jar file, which will then launch a nice little GUI. It's a little cutoff. It's all right. You can look at the approximated source code here, or I prefer to use the save all sources functionality on the left to save a zip file locally, and then I can play around with it from there. So at the top, we have a zip file on the right. That is the file resulting from JDGUI. We would then want to unzip that quietly to a directory called src. You can see that toward the middle there in blue, src. Within this directory, there are multiple files and subdirectories. The ones we care about are going to be in a directory that is a directory structure named similarly to the name of our package. In our case, the package is com.example.wmclaughlin, that's me, .patchtown, that's the name of the application. So we list that directory, and we get 5 Java files holding the approximated source code. R.Java we don't care about. It's automatically generated as part of the Android build process. Build config we also don't care about because it's not specific to this application. So we're left with 3 files. Key pin store, login activity, and PinTask. These are the 3 files that are going to hold the logic that we need to change. Recapping. Started with an APK. We converted it to a jar file. We decompiled this jar file. We analyzed the directory structure and determined which classes we need to look at. Next step is to analyze the source code in detail. Our goal here is to find the logic that is handling the pinning and figure out how to circumvent it. Tools for this, any text editor can be used. I'm going to be using Vim. Our targets are the 3 files we identified. First up is this key pin store file. So we open it up, and the first thing we see is a couple class members. So we have a key pin store instance, which is null. And importantly, we have an SSL context variable. This is important because SSL contexts can be used in certificate pinning, as per the official Google documentation. As an example online, they use an SSL context with a custom certificate within it. After that, we have the constructor on line 25, and it throws a whole bunch of exceptions. So we're going to hop into that function, get a better look. This is a lot of code. We're going to step through it real quick. First thing that happens is a local object called localObject2 is declared. It is a certificate factory of type X509. Next, we have a buffered input stream that is opening a file called security-evaluators.crt. Now, this is likely the certificate that the Android application is pinning. We know that because I work at security-evaluators.com, at security evaluators, right? And it ends in .crt, which is a typical certificate file extension. So now we have this giant try block, and it's doing a bunch of stuff. It starts off by generating a certificate object using this buffered input stream that contains the data from the certificate file. We got line 33. It looks like a little bit of debug output that a developer left in. After that, we're closing the input stream because we don't need it anymore. It's been loaded. And then line 35 is interesting because there is a key store being created with default parameters. Line 36 is doing some more default operations on that. And then line 37 is adding a certificate to this key store. The name of this certificate is CA. The data is the object that is the data that was read in from the file, security-evaluators.crt. After that, a trust manager factory is being created. On line 39, it is being initialized using this key store. And then on line 40, there's an SSL context being initialized using this new trust manager. So a custom SSL context that in the end is using the one certificate loaded from the security-evaluators.crt file. Within this class, there is also 2 smaller functions that are important. There's a getInstance function that will either return an instance of keyPinStore that already ran through all those steps we just talked about, or it will create a new one and then call the constructor running through all those steps, setting up the custom SSL context. And then there is a getContext function on line 63 that simply returns this custom SSL context. Cool. So the important thing here we have a custom SSL context. It's initialized with a custom trust manager that contains a key store that only trusts one cert, the one from this CRT file that we loaded. And there's also a couple getters. Next, we're going to take a look at this login activity class. So we open it up. Right away, we can see it looks like a pretty normal class. It extends app compat activity. It suspiciously looks a lot like the Android Studio default login activity. I won't elaborate on why. But the onCreate function is what's going to be called when the activity starts. So this is where we're going to look first. A lot of stuff going on in the beginning. None of it seems very interesting. However, on line 45, we're defining a onClick listener for a button. If you remember the screenshot from the beginning, there was one button. There's an email field, a password field, and a button. When the button is clicked, that's when the cert check happens. So this is what's going to happen when that button is touched. We can see that there is a function called attempt login that is being called. So we're going to want to look at that. The attempt login function is a one-line function. It calls execute on a new pin task. All right, simple enough. We have a login button with an onClick listener that calls attempt login, that in turn calls execute on this new pin task object. So clearly we want to look at the pin task class. So open it up. We can see right away that it extends async task. So in Android, an async task is basically something that's going to be run in the background so as to not block the main thread. By default, you'll be getting errors if you try to compile an app that is doing networking on the front end. So it's pretty safe to assume, especially considering we know what the app does, that this task is going to be handling some network communications. Probably the pin checking, the cert checking. So the first function that's going to be called when this task starts is the do in background function. So we're going to pop open this function, and we see some stuff. We got a try block and some lines. So the first line, you'll see this get instance function that we just talked about earlier. This is going to return the key pin store containing the custom SSL context that trusts the one single cert. Next, an HTTPS URL connection is started, specifying the securityevaluators.com website. So it's pretty safe to say here that this website, securityevaluators.com, is probably linked to that CRT file because they have the same domain, the same name. So what happens here is, on line 24, we're calling getInputStream on this new connection to securityevaluators.com. Two things can happen with this function call. This function will either return no errors, so it will make the connection, grab the cert, compare this cert to the cert in the key pin store. If things are in agreement, if the certs match, then everything's fine. The function finishes, and the program continues. It'll continue line 25, and then 26, and it will return an integer object with a value 1. However, if there is an exception thrown, if the certificate check fails, meaning that the certificate received from the server is bad, maybe it's a Burp Suite server certificate or something like that, when it's compared against the one that's stored and trusted, an exception is thrown. Something like a bad certificate exception. I can't remember exactly what it is. So when that happens, the flow will change. It will jump down to the catch on line 28. And you'll see that the exception here is named param_var args, and it will simply return this exception. So we can either return an integer with value 1 on success, or it's going to return the exception itself on failure. So when I say return, what happens is this return value is sent to another function called onPostExecute. This function is automatically run after the async task completes what it needs to do. So either the exception or the integer comes into this function, and one check happens. Is this an exception? On line 36. If it is, a function called cert validation failure is going to be called. If it is not an exception, for example, if it's an integer with value 1, cert validation success is going to be called. So basically, if the certs don't match, cert validation failure is happening. And if they do match, cert validation success is going to happen. Good cert means successful execution, we get the success function. Bad cert, we get an exception, and we get a failure function. The important takeaway here is this is what we want to change. We want to make sure that this failure function is never called. We always want success. So recapping the whole source analysis section. We discovered there was a custom SSL context. It trusts a single cert. We located the code in the pin task that performs the cert pinning. And we have now identified what we need to change to get this application to do what we want. The next step, before we actually patch it, is we have to decode the application. To do that, we're going to use APK tool. It's a pretty neat little toolkit. It does a lot of stuff. We're going to be using it specifically to get some smali code representation of the compiled classes. So this command, it's going to look like this. We have our APK up there on the left. We're going to run APK tool D for decode against it. It's going to do some stuff. And then it's going to give you a directory with the name of the APK. In our case, it's Patchtown. Very similar to the structure of when we decompiled earlier to get those Java the Java files. We're going to have a smali directory, which is going to contain the smali code, which is what we're going to be patching. And within that, there's a subdirectory structure of com, example, W McLaughlin, Patchtown, just like before. And within that folder, we have a bunch of smali files, each with at least one per Java class. So we know the ones we don't care about. We don't care about the R ones. We don't care about build config. And we do care about the ones in red, but in particular, we care about PinTask because we already identified exactly what we want to change. So let's do it. Our goal here is to modify the execution of the app to do what we want. We want to avoid the cert pinning. We want it to always succeed so we can use whatever cert we want. Call it a day. Again, I'm going to be using Vim. Any text editor will do, or any text editor will do. So this is the contents of the PinTask.smali file. You can see it's a lot more readable than like a typical assembly file would be, but it's not nearly as readable as Java code. Luckily, we don't have to look through this entire file, which is, I believe, 288 lines, because we know what we want to look for already. We already know that we need to be in the onPostExecute function, because that holds the function calls for success or failure. So we can do a quick search for onPostExecute. It's going to bring us right to line 209. And within this chunk of code, we have two key parts. You can see there is an invoke virtual, a bunch of stuff. And then you see cert validation failure at the end of the line. Further down, you can see cert validation success. So this is the equivalent code to what we were looking at earlier. If this is an exception, fail. Otherwise, succeed. So in order to patch this, the process is simple. We simply change failure to success. Before we were failing, now we're succeeding. So now we have the proper smali function calls set up. We chose PinTask as our target class because we knew the cert validation functions existed in there. We found the exact patch location in onPostExecute, and we've now patched our application. So before we can actually test this, we're going to have to rebuild the application. Thankfully, APK tool, magical thing it is, can rebuild our application. We're going to be using the B command, which is build, essentially the opposite of decode. Specifying our directory, Patchtown. We're going to be specifying an output APK. Call it patchtown-patch.apk. Run this command. Everything looks good. Do a quick ls. On the right there, you will see our new APK. Now, before we can install this, to do a couple quick intermediary steps, we need to sign the Android application. So to do this, there's two things we have to do. One, we have to generate a key store. And then two, we have to sign the APK using this key store. So to generate the key store, we can use the Java key tool command. We're going to tell it we want to generate a key pair. And we're going to name our key store patchtown.ks.keystore. We have an alias for our particular certificate we're creating, which is Patchtown. And we're going to tell it to use RSA. Cool. So we generated a key pair. It's stored in the file patchtown.ks. Now we need to use this file to sign our Android application. And the reason we need to do this is that Android cares that all packages are signed, but it does not care at all by who. So we can make up whatever key store we want, and then as long as the application's signed, it's good to go. You can install it. So to actually sign it, we're going to be using jar signer, specifying the signature algorithm, the digest algorithm, using our key store on our patched APK with our alias. for the certificate that we created. So we have an app, we have an APK file, it is now signed, it is ready to be installed. We can do so using the Android debug bridge install command, passing our file name as the sole parameter. So now it's time to test. In this scenario, I now have a custom Burp Suite certificate installed on my Android device. I am telling my Android device to proxy all traffic out of the device, point it toward my Burp Suite install on my desktop so I can view any outgoing web requests. Normally, initially, the application would connect. It would get the Burp server certificate, realize it's not what it's expecting, and break. It would fail and it would exit. This time, though, it does not. We get the success message we noticed before, and it looks like we're good to go. Our patch seems to have been successful. The way we test that is we can look in Burp to see if any requests are going through it. If they are, then we know that the patch was successful. Thankfully, when I looked in Burp, it did. The initial request to securityevaluators.com hit my proxy, meaning the certificate pinning was circumvented, and we can now view any traffic going in between the app and the server. Any web requests. So, full recap of what we did here. We started with an APK, we decompiled it. We got the approximated source code that we were able to look through and identify key parts of the code, key parts of the logic that we would need to modify in order to get the app to do what we want. We decoded the APK using APK tool. We located the patch point that we initially saw in the decompiled source in the .smali code. We edited the .smali code, replacing the get the certificate failure function with the certificate success function. We rebuilt the application using APK tool again. We signed it using key tool and jar signer, and we tested it. And we saw success. So this talk was initially a 50-minute talk. I got accepted as a stable, so I had to chop a bunch of stuff out. I was initially going to talk about some Java native interface patching stuff. Basically allows you to use C++ or C code in your Android application. But unfortunately, I had to cut that out. But if anyone has any questions about that, maybe you can meet me in the hall. We could talk about it. I'll be upstairs in the Derby room as part of the running the IoT village. So feel free to come up. Another caveat that recently came up with Android 7 Nougat. It's not as simple as installing if you want to intercept traffic, it's not as simple to just install your custom proxy cert into the device and then do what we did to allow the connections to work. Now apps by default will not be using the system store, the system certificate store. So there's a line in the Android manifest you'll have to add. Can't remember what it is right offhand. But it's easy enough to add it in. You just gotta decode the application like we did, edit this one file, rebuild it, sign it. There's some mention of this online, so if you want to look into it a little bit more, it's there. I hope you guys learned something. My goal of giving this talk was I know when I first wanted to patch an Android application, I was like, I don't have any idea what the hell I'm doing. Right? I thought it was going to be very difficult. Hadn't really done it. Was kind of intimidated. But as I got into it, I realized it's not as bad as it seems. And I hope that I got that across to you guys. So thanks for listening. I hope you learned something. If we have time for questions, I'll take them here. If not, you can talk to me in the hallway or upstairs. Any questions? Okay. Well, thank you.